So maybe we can slowly start while people are still entering. So good afternoon, everyone, and welcome to this next talk of the DGA series. It's our great pleasure to have today Stephanie. So Stephanie is a faculty member at MIT in the Department of CS. Before she was a postdoc at UC Berkeley, and she obtained her PhD from the ETH Zurich and also from Max Planck Institute for Intelligent Systems. She has received various awards, including the Sloan Research Fellowship, an SNSF Career Award, a DARPA Faculty Young Faculty Award, a Google Research Award, and many others. And her research interests span the theory and practice of algorithmic machine learning, and in particular, learning problems that involve combinatorial structures such as networks and graphs. So Stephanie, thanks a lot for taking the time to present today, and we're looking forward to your talk.
Thank you very much, Dorina, for the introduction, and thanks for the invitation for having me here speak here today. So today, I chose to talk about our work in learning and extrapolation in graph neural networks. So graph neural networks are a neural network architecture that has been very successful in practice, and slowly also some theoretical developments are happening, and I'll show you some of these today. And I'll explain what are graph neural networks and what kinds of problems we can address with them so that we're all on the same page. So let's start with examples of learning problems on graphs that we may want to address. So one example is that the input, each data point is a graph, and we want to predict a label for that graph. So this could be a category, it could be continuous. So one example is that this graph is a molecule, and we want to do property prediction of this molecule, like is it solvable? Is it toxic? Would it work as a drug? Would it react with certain substances, etc.? So that's become a very important problem in drug development and material science, etc. Another example is when we don't really have a graph as an input, but we have a configuration of items as an input, like a set of particles that are in a certain configuration. And in this case, we want to essentially predict the next state of that system of particles. So essentially, we want to learn a simulation. So in this case, we can build a graph from that set of particles by connecting the nearest neighbors and then predict the next state based on that. And then there are problems where we actually want to make a prediction not about the entire graph, but about parts of the graph, like a node or a pair of nodes. So one of these is link prediction. And in this particular example, the task is to predict interactions between drugs that you're taking together. So you have a network consisting of proteins, consisting of drugs, and have links if they interact. And you want to predict basically if there's an interaction that if you take these drugs together, you'd actually have an adverse side effect. And another link prediction problem is recommender systems, where our graph is bipartite. So we have users on one side and we have items on the other side, and we want to predict whether a user would like an item, which would be another link in this network. So there's many such tasks, and what we actually need to make good predictions in these tasks is two things. The first thing is capture something about the structure of the graph, basically the relationships between the items, because that's what we deem as important, like the bonds between the atoms or the interactions between drugs and proteins as we know about them. And the other part, apart from the structure that we want to keep information about, is any side information we have about nodes or edges in the graph. And so we want some model that captures both of these in some way and essentially takes as input that structured object as like the graph and gives us a good representation of nodes and of the entire graph. And there's many more applications where this actually is useful. I'll be talking a little bit about the combinatorial optimization part, but there's many, many different applications. So that's essentially what our graph neural network is going to do. So it's going to take a graph, and it's basically a function that takes as input graph and predicts something. And it's going to use to compute a good embedding of that graph. So the way this learning problem is typically set up is that I have training data. Let's say I want to make a prediction about graphs. the input, each data point is a graph with a label, and then I'm learning to fit a function. But now, if I actually want to understand how graph neural networks learn and what they can learn, and this is essentially the topic of my talk today, I need to think about a few things. So the first thing is, well, what we actually care about is not really making a good prediction on the training data. That's also one thing, but we also really care about making good predictions on test data. So data from the same distribution generally. So that's called generalization. So to understand the generalization power of a model, we need to ask a few questions. The first question is, well, what can my model class encode at all? So that actually also relates a lot to how well can you fit the training data. So what kinds of functions can I even encode in the best case? So that's the question of representational power. And the second question is, so even if I can encode this function, I have to actually find and identify the right function. So how much data do I need? What kind of data do I need? And how does the model architecture affect how much data I need? And what kinds of functions I'm more likely to learn? So there's always some biases that you implicitly encode in this architecture and in the learning process. So what are these kinds of biases? And finally, one question that has become actually also of great interest is, how will my model perform if it sees different data that looks different from the training data? So this is out of distribution generalization or extrapolation. And in this case, I have to ask, well, what does my model actually use about the data, and what does it mean for that other data? So I'll be talking about that question also in the end. So here's the outline of my talk for the rest of the talk. The first, we'll think about what is a graph neural network at all, and then we'll be thinking about those questions that I just posed on the previous slide. So the first question will be, what can a graph neural network represent? What kinds of functions on graphs can it actually represent, and what can it not represent? The second thing we'll be thinking about generalization and the interaction with the architectural structure of the model. And then we'll see how this actually extends to thinking about extrapolation. And extrapolation in graph would be essentially here in my little picture. Normal generalization is training and test data come from the same distribution, and extrapolation is that you're coming really from somewhere else. And in a graph, this could be graphs you're training on small graphs, you're trying to generalize to larger graphs or to graphs with different distribution, degree distributions or so. And at the end, we'll be looking at aspects of all of model architecture, data and task, and the training algorithm. But let's start with what is actually a graph neural network. So as I said, the graph neural network tries to find an encoding or embedding of the graph that captures both the structural information in the graph and any side information that we have. So typically what we assume is that each node in the graph has a feature vector or an attribute vector associated with it that describes some properties of that node. Like it could be describing some properties of an atom in a molecule, or a user in a social network, etc. And then we have the graph structure. So and I'll be describing here a specific architecture of graph neural networks that I'll be using going forward, and these are message passing graph neural networks. And those are likely the most widely used graph neural networks. So they work in two phases. The first phase is encoding each node, finding a node embedding for each node that encodes its local neighborhood structure. And the second, so what we get is, we get a vector representing each node's neighborhood. And then we take that set of vectors and we aggregate it into a representation of the full graph. And this is also called the readout step. So that readout step could be as simple as just taking the average of these vectors, or it could be something more complex. And the important part of this is that this is what's called permutation invariant, in the sense that if you would change the order of those node representations, you would still get the same graph representation, because that would be basically corresponding to permuting the rows and columns in your adjacency matrix. So the other question I haven't talked about is, like, how do you actually get this node embedding? And the node embedding is typically done via a learnable message passing algorithm. So it goes in rounds, and in each round, each node collects the current representations of its neighbors and updates its own representation according to that. So this is called the aggregation step, and that's kind of the central part of this graph neural network is this aggregation step, and that's the actual thing you're learning. So what the aggregation step does, it takes the current representations of the neighbors and it applies the function that goes from a set of vectors to a vector. And this function has to be also permutation invariant in the sense that there's no natural order between the neighbors. And then once we have computed that joint representation of the neighbor, we use it to update the node's representation, and that it can be as simple as a weighted combination. So this aggregation step typically is encoded via a small neural network itself. And now we do this over rounds, and in each round, each node uses the same aggregation function. And if we have like 2 steps, we already encoded 2 hop neighborhood, etc. And the central part, as I said, is this aggregation function. And this is typically encoded as a small neural network itself. So when I write MLP, I mean a small, fully connected neural network. So that's the part that we're learning. And in the combined step, we also learn maybe the weights and with some nonlinearities. So that's the central part, is this aggregation step. And that's what we have to learn. So now I call this a neural network, and you see it has a small neural network inside it, but let's look at this so that it looks even more like a neural network with layers. And the different layers will be just the different rounds or the different iterations of this message passing. So here's how we could illustrate it in a different way. So that's the same process, just written in a different way. So let's say we want to compute the representation of this target node A. So now let's just see what we actually did to compute this representation. So A collected information from its neighbors and did this aggregation to update its own representation. So I here illustrate this aggregation with a gray box. And in the previous iteration, each of the neighbors collected the information from their neighbors and applied an aggregation function. And they all apply the same aggregation function in the same round. So now as you unroll this, you see this looks like layers. So it looks like more like a neural network, where just the gray boxes are your learned aggregations. And the only difference to like more common neural networks is that the connectivity structure depends on your input graph, because those are the neighbors. So you could think of these as layers. And now we do weight sharing, so we share the aggregation functions within the layer. Now I'm sort of pushing this viewpoint because this view will also be useful in understanding what graph neural networks can and cannot do. So this is also called a computation tree. The other thing that actually you can see here, like in this abstraction, it looks like a structured arrangement of some learnable parts. So my learnable parts are the gray boxes, the aggregation functions, and the computation tree structure is fixed. That depends on my input graph. So that one we are actually not learning. And someone asked, how do you share the weights in the aggregation function? So you're basically applying the same aggregation function on each neighborhood. So that's the same as when you're in a convolutional neural network, you're using the same filter on each patch of the image. So it's exactly analogous to a convolution in that sense. Okay. So now that we have understood the big picture of a graph neural network, let's think about some of the properties of these graph neural networks. What can they learn and how do they learn? So the first question is representation. And I just see there's an important question in the chat about different nodes have different number of neighbors. And that's actually an important part to understand. And that's why the way you can actually have this aggregation function is very restricted, in the sense that an aggregation function, this gray box, must be encoded in a way that it can take 2 vectors, 1 vector or 100 vectors as input. And the way you achieve this is that you actually learn in your functional form, you learn Let me show you this one. So you learn a nonlinear function, but you apply it to each neighbor individually. So to each neighbor, you apply the same nonlinear function, the same MLP, and then you sum it up. And that way, if you are doing this to 100 neighbors or 2 neighbors, that's the same thing. Like you learn this MLP once and you apply it to each of the neighbors. So that way you achieve basically something that can take 100 neighbors, it can take 1 neighbor. And that structure is going to be important. Okay, so hopefully this became clearer now. So now let's think a little bit about the representational power. And the way representational power is analyzed in graph neural networks is often a bit different from other neural networks. So often we think about universal approximation, that there's like some continuous functions and we can represent essentially all continuous functions. So the problem is here we have graphs, and what's even a continuous function on a graph? That's a bit more tricky. So the first thing people typically analyze is what kinds of graphs can be distinguished. And based on that, you can actually now think about classes of power of representing specific functions on those graphs, in the sense that if 2 graphs are assigned different embeddings, I can assign them different labels. If 2 graphs are mapped into the same embedding, I can only ever predict the same label for them. So I cannot distinguish them. So that's the main idea. So the first thing to think about is what kinds of graphs can I even distinguish? And that's actually a hard problem. That's the graph isomorphism problem. So that's a hard computational problem. And to understand how far graph neural networks can go with this, we have to go back and think about how does a graph neural network actually see a graph. So I showed you these computation trees, and essentially the graph neural network sees your graph as a collection of these computation trees in the best case, because that's how essentially each node representation is encoded, as computed. So that's basically the maximum information it has. And now the question is, how informative is this set of computation trees, rooted at each node? And in this graph, it looks actually that it's a pretty good fingerprint of that graph. But now if you think of graphs like these ones, where all the nodes, so different colors here denote different node attributes, all the nodes are kind of indistinguishable per se in their attributes, and say you have a regular graph, each node has 3 neighbors. In this case, all the computation trees will look exactly the same. These are not the same graphs. You can see one actually has a triangle and the other one doesn't, but you cannot actually distinguish them with computation trees. And so you can actually formalize this a bit more. So on regular graphs, it won't work. That's already sort of my picture showed this, unless you have some distinction between the nodes. And in general, they are basically in the best case as discriminative as a well-studied graph isomorphism test, which actually also works in kind of this message passing way. And the only thing it does is it hard codes this aggregation via hashing. So in the best case, you can be as good as that, but not better. And this is very well understood. And the good news is, out of all possible graphs, it can distinguish a very large fraction. But it has like known failure cases that have these regularities. The other thing is, though, that even if in the best case I can be as powerful as this test, it doesn't mean that all graph neural networks are as powerful. And how actually discriminative you can be depends on this aggregation function that I stressed so much. And in the sense that if you want to mimic this thing that does hashing, you have to have an injective function, meaning a different set of input vectors is going to be a map to a different output vector. So you can distinguish all possible sets of input vectors. And now you have to find, basically for that, you have to have an encoding that can represent basically any such set function. And you can show that an encoding that can do this is to have a nonlinear function sufficiently powerful applied to each input vector, then sum them up and have another nonlinear function. And if these MLPs are powerful enough, then you can represent all injective multiset functions. So multiset here means that the entries in your set can repeat. So that basically tells us that if we encode our aggregation function in that way, then we have the potential to achieve that discriminative power. You may not actually get it because you learned something else, but in principle you can. But many of the graph neural networks that have been proposed initially do not have this power. So they use, say, not a sum here, but an average or a min or something, and then this becomes harder to do. And sort of to illustrate the empirical impacts of this, so this is the theory, but the question is, does it have any empirical impact? Let me just show you one quick experiment on this. So this is sort of the, in some sense, best possible representation for this message passing network. And now what we need is, we need some sufficiently powerful nonlinear functions here, and we need the sum here to be injected. So now what we'll do is we'll make these less powerful, the MLPs, or we swap the sum for something else. And what we see here is a benchmark data set, and we see the training accuracy. So one is basically you fit the training data perfectly. And if you use the sum and the MLP, you can fit it perfectly. You reach the accuracy of 100%. But if you make, for example, the MLPs weaker in that you actually have just a linear function with a ReLU, or instead of a sum, you use a mean or so, an average, then you're actually not as discriminative. So you cannot actually even have good accuracy in fitting the training data set. And these generally also extend to test error. So this is training error because it's just fitting, but they also extends to test error. So these actually do have an impact in practice too. So someone asked, does the small MLP approximate the data well? So that is actually true, that typically the MLPs that are used in graph neural networks are more like few layers, and of course not infinitely wide, but that appears to be sufficient for most tasks to fit them well. In theory, yes, that does not actually fit well any possible continuous function, but it seems to be sufficient, at least compared to this more simple representation. So that sort of says, okay, this is actually already giving us a relatively good approximation power for different functions. But I want to show you one thing that you can actually not do with message passing networks. And this is particularly relevant to tasks in computational chemistry and drug design, where we may have these molecules and we may want to actually really encode, does this molecule have a 5-cycle? Or 2 rings that are together or something like that. That's the conjoint cycle. Or count some motifs. And what you can show is actually that in general, these message passing neural networks are blind to those kinds of features. And I already actually showed you one example with these 2 regular graphs where I said one has a triangle and the other one doesn't, and you cannot distinguish them. So obviously you cannot count triangles, because otherwise you would be able to distinguish them. So that's essentially the idea of the proof, that with these computation trees, you cannot actually discriminate based on these motifs. And this is bad news in the sense that if we want to make those predictions from molecules, often those are presumably very important features. And to actually take care of these, you have to basically change something about your graph neural network. So people have been looking into ways of making them more powerful. And one idea is to go higher order. So instead of, for example, passing messages between nodes, you can pass messages between subgraphs or subsets of nodes. And there's other things you can do. You can do more general, like generalizations of invariant functions or recursion or so. Or you can actually keep the message passing, but you can make the nodes more distinguishable by introducing node IDs. That has a little bit of the challenge, though, to make it actually invariant to, like, if I give you the same graph and I just permute the order of nodes, does it still give me the same representation? So that you have to make sure. But that's still like an interesting area of research. How can you actually be more powerful while still being computationally not too expensive? So some of those higher order models are pretty expensive. Okay, so this was a little bit of a thought on what kinds of functions can I represent with my graph neural network in the best case when I had basically infinite amount of data and I can fit anything I want, if my model class is powerful enough. So next, I want to think a little bit about that data aspect and about generalization. So what helps now accuracy on data points that go beyond your training data set? And we'll first look at data points that live in the same distribution as your training data. And there have been several works on trying to get generalization bounds for graph neural network. So the first set of works essentially goes via more standard ideas from learning theory, like random macrocomplexity, for example, the C dimensions, and trying to bound those for graph neural networks. And the challenge there is that it actually looks like the fully connected networks, but the connections are more irregular. So they are more local, just like in CNNs, but they are more irregular in the sense that one node can have 10 neighbors and one can have 100 neighbors. And you have this specific form of the aggregation function you want to take into account. So you have to take all of this into account. And those norm-based bounds actually show some interesting relations to recurrent neural networks, because in some sense you can view a graph neural network as a generalization of recurring neural networks. And the next step was that, okay, norm-based bounds, they don't actually think at all about, say, the training procedure. They just talk about the complexity of the functions. So to take the training procedure into account, that's in general difficult for neural networks, but it does matter a lot for neural networks. And so that has been done via using ideas from the neural tangent kernel framework. And both of these are useful for more simpler functions that I want to learn on graphs. But sometimes we want to have tasks that are actually more complicated and where it's a little bit harder to get hold on, like a more of a functional norm, or so it's a little bit abstract for these tasks. So those are more structured tasks, and I'll show you some of them that look more like algorithms. And for learning these algorithms, actually we can have, say, a bit more about the structure of the architecture and the structure of the task. And that's where I want to go next, and that's the work that I'm going to present. So these are the tasks that are generally called algorithmic reasoning tasks. And those are tasks that often can be where, like, if you actually wanted to compute the right answer, you actually run an algorithm. So these could be questions such as comparing objects. So you have a set of input objects, and you want to say, well, what are the colors of the farthest pair of objects? So you have to look at the colors, look at the relation of the objects and compare them, and based on that comparison, compute something. It could be those physics simulations where I say I have a set of items and they interact in some way, like these blocks, and what is the next state of that system? So I have to essentially learn this laws of physics here. How they interact based on their velocity, based on their acceleration, their location, etc. Or it could be something like learning graph algorithms. So a recent line of work has been aiming at learning full algorithms or parts of algorithms with graph neural networks. So you could actually try to mimic a full shortest path algorithm with a graph neural network. So for example, this survey paper has a lot of examples of such kinds of tasks. So the general framework, a bit more abstractly here, is that we have this universe of items, and it could be already connected as a graph, or it could be just a universe and we can make a nearest neighbor graph or so. And so basically each of these items is encoded as a vector already. So I do not actually do image recognition here. I just assume that I have an encoding of each of these items. And then I send them through that reasoning network and get an answer. Like, this is my physical system, and I get an answer, what is the next state? So the question is, what should go in this reasoning network? And this is sort of just as a motivation of thinking a little bit about the structure of the task and the structure of the architecture of my model. So I will focus mostly on this red box here, what goes in that red box. And so for just like doing a neural network on a set of items, there's various choices I could think of. So the first one would be, well, I have this set of items. I have a vector representation for each item. So I just concatenate those and I send them through a fully connected neural network. That works, but it has the disadvantage that if I would now permute the order of my items, that's actually a problem in the sense that the MLP has to learn that this should be the same thing. It's the same universe. So don't be indifferent to that. And a model that already encodes that indifference to permutations, this permutation invariance, is the so-called deep sets model. So what it does is it applies, so I sort of illustrated this here, the gray boxes are my small neural networks. It applies a small neural network to each of my items, so a small fully connected network. And then it sums up the representations and then it applies another nonlinear function, like another small neural network. So this doesn't care about the order of your inputs. And this actually looks like a single aggregation function in some sense. So that works better. And then we could actually also encode this as a graph. We just could, for example, make a fully connected graph and make a graph neural network on these, just in the way that I told you. And typically here, people, if I apply a nonlinear function to the neighbor, people use the center node also as an argument to that function. So this is the same thing. This is my aggregation function. And in the end, I aggregate everything. So sort of what this is doing compared to the deep set, it's doing like pairwise reasoning. I only look at pairs of nodes always here, like at the center and a neighbor and the center and another neighbor, do this aggregation. And then I do this in multiple rounds. So it's a more structured pairwise reasoning. Now, these are things that I could use for the tasks I showed you. And what people have found empirically is that even though theoretically you can actually show that if one of them can represent such a reasoning function, the other networks can also represent it. So in some sense, they all can represent similar things. Empirically, when you do learning with them, there's big differences in how well they do. And so basically the graph neural networks perform the best on these tasks. And like, so going from left to right, you get better and better. So why is this happening? So this is sort of, people have thought about this as like inductive biases from the architecture, but we wanted to think about it a bit more quantitatively, a bit more formally. So why may this be happening? And one idea is that intuitively, if you think about learning this physics system or learning a shortest path algorithm, what you're actually, the end task essentially is something like an algorithm. So even the simulation, I could say, like going from step to step, it's like a big for loop, and going from step to step, I have a certain update of my states. In the shortest path, also it's the same thing. So I basically have an algorithm. And what is an algorithm? An algorithm is a structured arrangement of some subroutines. Like the for loop is a structure, and then in the for loop I have some subroutines. Now a neural network, as I drew them here, could also be viewed as a structured arrangement of learnable parts, and the learnable parts are these gray boxes here, your small MLPs. So then the idea is that if basically the computational structure of this neural network and the algorithm match in some sense of matching, then the learning should be easier, because you don't actually have to learn the structure of the algorithm, just the subroutines. And let me show you one example to make this clear. So this is the shortest path algorithm, which will be my running example, the Bellman-Ford algorithm. So what it does is, you probably know it, it goes also in iterations, and in each iteration, each node updates its state, and what the state encodes is the shortest path to the target, the currently found shortest path to the target. And in each iteration, you update that state by looking at your neighbors and looking at, hey, if I go through that neighbor, maybe I could get a shorter path. So that's what this operation is doing. Now, if you look at a graph neural network, it has actually very much the same computational structure. In each iteration, you do something for each node, and you update that node's representation. That's like the state. And the only difference is that in the graph neural network, you have that aggregation function. In the Bellman-Ford, you have this relaxation step. But now, if your aggregation function would mimic that min over the neighbor step, then you have basically implemented the Bellman-Ford algorithm if you run enough iterations. So if your network is sufficiently deep. So the idea, the intuitive idea is that in that case, this thing has to learn a very simple function. The min and the plus is pretty simple. It's not such a complicated function. And the rest is already there. The rest is hard-coded, so you don't have to learn it. So presumably, in that case, when these structures match, then you should be able to learn with fewer samples. You should be able to learn faster. And we call this algorithmic alignment. So algorithmic alignment means that a neural network can mimic an algorithm via a few easy to learn modules. So your modules are the gray boxes, or basically these little learnable neural networks here. So how does this actually look like in practice? So if you look at some empirical results, so here is an experiment on learning actually a shortest path, or like some variation of the shortest path. It was actually a bit more complicated with these different models. So for just the fully connected network, it didn't really work with the amount of data we gave. For deep sets, it was a bit better, but not that much. For graph neural networks with one iteration, didn't really work that well, but up from like 3 or 4 iterations, it actually worked. It actually learned well, and this is test error. So in those cases, actually, the shortest path was about the length of 7 or 8. So this like 3 or 4 is essentially half the length of the shortest path. And you could implement a bidirectional Bellman-Ford to get basically a shortest path in that many iterations. So this could be an explanation that very well aligns with our idea of algorithmic alignment. But now let's make this a little bit more formal. So this was one example of the Bellman-Ford algorithm, and you saw that kind of it matches, like empirically the graph neural network does better in learning a shortest path. And this is like for any kind of graph. But let's look at this more generally. So actually more generally, graph neural networks could be viewed as implementing a dynamic programming algorithm where you go in rounds, and in each round you update states. So each node in this case has a state, and you update the state. And if now the dynamic programming update of your target function is simple enough, you should be able to learn it fast, in the sense that your aggregation function has to mimic the update in the update step in the dynamic program. And if you think about, for example, the shortest path, the update is not such a difficult function. In many of the physical systems, you can have an update that is not too complex for the next state. So many physical systems can be described as these essentially dynamic programming procedures. So that could be an explanation why graph neural networks have been working so well for these algorithmic and physical reasoning tasks. But let's try to make this a bit more formal, because for the moment I was also a bit hand-wavy. I showed you some examples. So to make this more formal, so here is a definition, a formal definition of alignment. So now we have these parameters m, epsilon, and delta, and they come from the PSC, from the tag learning framework. So what it basically means is that m is for the number of samples. So now I look at each of my modules, each of my shared aggregation functions here, and I see how many samples would I need to learn basically that update operation. And I learn it in the tag style, which means with probability 1 minus delta, that's where the delta is, I make an error of at most epsilon. So that's the epsilon here. And then I basically look at all the samples that I would need for all of those pieces, and I put them together, and that's the big M. So that's a way to quantify it. And now how do I get the sample bounds for the pieces? Well, you could use any analysis framework you want for getting there. So you could use a neural tangent kernel or something else, because we have these MLPs. So this also leads to actually a generalization bound. And informally what this theorem says is that if I have a neural network and a target task, which essentially corresponds to an algorithm, and they have the same computational structure in the sense that for learning all of the modules, I don't need too many samples, then under some assumptions, the entire task can be learned well. So if the modules can be learned well, the small subroutines, then the entire thing can be learned well. And this makes a few assumptions. Some of these are more standard, like things are Lipschitz continuous. The hardest one is the layer-wise training, which we couldn't get rid of, but in practice, you don't actually need layer-wise feedback. And this gives you actually gaps really between fully connected and say graph neural networks for certain tasks. So what essentially this theorem says is that if you have an alignment of the architectures, then you should be learning better. And this is essentially what we see in practice too. Okay. So next, I will extend this viewpoint and think not only about in-distribution generalization, but out of distribution generalization. So this is called extrapolation. And extrapolation has actually been an important topic in deep learning more generally. And so it could mean different things in different tasks. So I talked about these physical reasoning tasks. In that case, what it would mean is you train the neural network with a specific set of positions and masses and number of objects, and then you want to generalize to more particles, for example, or particles with a different mass, etc. Does it actually work? And that actually turns out to be pretty challenging. For graph algorithms, what it means is that I train maybe on small graphs, and I want to generalize to graphs of a different size or graphs with a different degree distribution, different type, different ranges of edge weights or node features, etc. And there's similar generalizations for other types of tasks in deep learning. So that's an important question, and it turned out to be pretty challenging. And sometimes it works and sometimes it doesn't work. So the question is, under what conditions can we get this to work? And obviously, normal learning theory doesn't extend here anymore, because normal learning theory assumes that training and test distribution data have the same distribution. And in this case, training and test do not have the same distribution. So you're really going away. So the question is, first, to understand what does your neural network actually do if you go away from your training distribution and look at data that looks very different. What kinds of functions does it actually implement? And for graph neural networks, people have observed empirically that sometimes this can actually work. So you can actually extrapolate the task that you actually want. Sometimes it doesn't. For fully connected networks, usually it doesn't. And of course, the problem is that I have my training data here and I have some test data somewhere else, and you don't have any feedback to the network what it should be implementing there. So it basically implements whatever is encoded in the architecture as sort of a bias, a learning bias, or from your training process. So what does it look like so the puzzling thing potentially is that MLPs are parts of graph neural networks. They are my building blocks, and they don't work, but graph neural networks sometimes work. So what's the difference? And so to understand that, let's first look at what does one building block in a graph neural network do. So now we first look at just the learnable part of this aggregation function, which is a fully connected network, a ReLU network usually. And so if you train a ReLU network, so these experiments are in simple functions that are typically like no graph tasks, just some toy experiments here. And let's say you train on some nonlinear functions like a quadratic or cosine function or linear or L1 functions. And what you see is if you go away from the training distribution, the nonlinear functions, it does actually, the prediction is pretty bad. And for linear and these piecewise linear functions, it sometimes works. And so there is something going on here between this linear and nonlinear functions. And we can actually understand this a little bit better. So what's actually happening is the following, that in your training data, this neural network can approximate like any nonlinear function. It's pretty good. But if you go away from your training data, it basically just implements a directionally linear function, meaning if I go away an array from my training data, it's just going to be a linear function. So that's this green line here, where the target is this sine function. And this also happens in higher dimensions. And this is something you can actually even prove. And it's, of course, based on the fact that we are using a ReLU activation function, which is used commonly. But similar things should be happening with other activation functions too. So the theorem we have here is that you can really prove this in a simplified setting when you have a two-layer network and you use the neural tangent kernel framework. So you take into account, to some extent, the training algorithm, that you really get that along any direction away from the training data, you are quickly approaching a linear function. So it can be different in different directions. So it looks something like this, but it's not going to be nonlinear. So if your target function is like a quadratic, you're not actually going to be approximating that well if you go very far away. So that's kind of interesting. So let me take a step back. So what actually determines what a neural network learns? We said the architecture, we already had this alignment. Then we have the training algorithm at gradient descent, which kind of gives us this neural tangent kernel framework and gives us these linear extrapolations. And then there's actually one more thing. I'm going to skip the details of the neural tangent kernel. The data itself, because say, even if it's okay that you learn just a linear function, the ReLU network can actually implement lots of different functions, and you need enough data to actually learn the right linear function. So in this example, we had data only, say, in the positive direction, and then in the negative direction, you have no supervision. It may be implementing some other linear function. So you need sufficient support in all directions. So going back now to our graph neural networks, there's two important points. The first thing is that when we think about our aggregation functions, what they actually do away from our training data is essentially a piecewise linear function. So all we can really implement outside of our training data is a piecewise linear function, or basic directionally linear function, so essentially linear. The second thing is that we need enough information in our training data set to identify the correct linear function if we work with an architecture where that's actually okay. So let's first look at the first point, that linearity problem. And let's now go back from the zoomed in version of our aggregation function to the big graph neural network. And as an illustrative example, let's go back to our shortest path. So what would this mean for a shortest path? So if you look at what our aggregation function should be mimicking in the shortest path is this min operation and the sum over the neighbors. That's the update step in Bellman 4. And we said actually our graph neural network with its sum aggregation and applying the MLP to each neighbor can mimic that, because, okay, in principle, if it's big enough, it's a universal approximator. This thing can mimic the min. But for this sum and nonlinear function to approximate a minimum, the MLP has to implement a nonlinear function. So that's the only way you can actually get approximate to a min. So this should work well on your training distribution, but based on what I just said, if you go away from your training distribution, this thing will become a linear function. So this may cause problems. And if you look at actually the literature, people who in papers where they actually did successful extrapolation for this task, they did not use a sum in the aggregation function. They use a min or a max in the aggregation function. And if you use a min, for example, then this MLP only has to implement the addition here, and that's a linear function. So you only have to learn a linear function. So the idea is that actually, if you now hard code the nonlinearities in your architecture and the learnable parts are really just linear, then you can actually extrapolate well. And this is what we call linear algorithmic alignment. So before we said we have easy to learn learnable parts, but now they have to also be linear. So that's even more restricted. And so both of these would satisfy alignment, but only the lower one would have the linear alignment. And now what does it look like empirically? So here are some empirical results. The pink ones are the linear alignment, where you learn a linear function, and the gray ones are the learning a nonlinear function. And you see that if you are doing normal generalization, so training and test have the same distribution, both of them have low error. This is the error bars. But if you do extrapolation, the pink one still works. The pink one has the linear function, but the gray one has to learn a nonlinear function, and that one doesn't work anymore. So you see the difference only when you go out of distribution and you look at graphs that look very different. And the reason is that if, say, your degree distribution changes, the input ranges to your aggregation functions change, and hence they go out of distribution. So your aggregation functions become linear, and that explains this plot. So what is the takeaway? The takeaway is if you do within distribution test data, it doesn't matter which one you use. If you do out of distribution test data, it matters. And what you actually have to do is you have to be much more strict about your architecture, and you have to encode the nonlinearity somewhere else. For example, directly in the architecture, like we did with this min here. So you need more prior knowledge. And this makes sense because you don't have any feedback signal on this data outside of your distribution. And if you look in the literature and look at empirical works that have been able to successfully extrapolate, many of them do exactly that. They have specific nonlinearities that they use so that the function they actually have to learn is much more linear across a variety of tasks. The other alternative is, instead of encoding it in your architecture, changing the representation of the input, like let's say in a physical system, the encoding of your nodes in the input, to make the learnable parts more linear. So that is also possible. And now this uses prior knowledge, or maybe if you use representation learning like self-supervised learning, this could also do something like that for you. Now, finally, I just want to say a word about the training data. I said, well, what's important is, one is the linearity of the function that you have to learn, and the other one is that your training data is essentially diverse enough. So what these experiments show is that if you just train your model on a specific type of graph, like only trees or only paths, and then you want to predict for all graphs, it may be too restrictive. So what you need is essentially enough diversity. So these are the types of training graphs. This is the error when you predict on general graphs. So you need enough diversity in your input graph distribution, for example, to be learning the right functions, even if you have linear alignment. So even when you have the strict conditions on the architecture, you still need the conditions on the data. And this particular theorem is an actual formalization in a simple task like learning just to predict the max degree in your graph. So in that case, if you really want to extrapolate, you need this linear alignment. So you use a max aggregation instead of the sum. And what you essentially need is that if you look at the statistics of your graph, so this, how many, like, what is the min degree in the graph and the max degree in the graph, and how often does it occur? That set of vectors for each graph has to, so if you take that vector for each graph and you look at all the vectors for all the graphs in your training data set, has to be spanning R4, so it has to have enough support in all directions. So basically enough diversity in the max and min degrees and how often they occur. So what does this really mean for extrapolation? And let me just say one general thing about that. So what I showed you was a very strict condition on the architecture so that this works. And that was in the case when you don't make any other assumptions on how similar your training and test data are. So that's basically one way in which you can achieve extrapolation, is that even if your training and test data are very different, you can achieve extrapolation if you make more assumptions that you put into your architecture. The other possibility is that actually your data distributions and training and deployment are still similar enough, like the small and large graphs are similar enough so that they essentially look the same to the model. And there's various ways of characterizing this and formalizing this. And the works that I'm citing here for spectral GNNs that use actually the eigenstructure of the graph and for message passing models have been analyzed in these other works. So this is more based on the assumption that the data actually look sufficiently the same in training and test. And those are the two, at least two ways how you can make extrapolation work. So with that, let me end here and summarize. So I talked about many different ways in which you can think about learning and graph neural networks. The first one was to think about representational power, where you think about analogistic graph isomorphism testing, and then generalization within distribution, where the algorithmic alignment was turning out to be important, and extrapolation going one step further than the alignment and thinking also about the linearity of the function. And of course, the structure of the data actually plays a role in both of these. So with that, let me end and see if there's any other questions. Thank you.
Thank you, Stephanie, for this very interesting talk. So feel free to ask any question. Well, there is already a hand from Hamid. So Hamid, if you want to unmute yourself, please.
Yeah, thank you. Very nice talk, Helena. It's a very refreshing talk. I do have a question more sort of at a high level, in the sense where when I look at a graph, I basically look at it as a dependent structure, representing a dependent structure of some process, right? So abstractly, what are we doing, particularly in the sense of the nature of the training data itself? What are we trying to do exactly when we're doing graph neural networks? Because I mean, I could see it doing that in some applications, but not so much in some other applications. What are we really learning?
Yeah, that's a good question. And what we are learning really depends on the task, what you like. So what does your graph represent? So you said, okay, for you, the graph often represents some process or so. So there's maybe even an order in your graph. So maybe in that case, you want to do some kind of, it depends what your prediction task is, link prediction, or you want to predict if that entire process is a task, maybe is an input data point, you maybe want to predict something about that process, how efficient it is, or something like that. So in that case, so if you think about efficiency of a process, so it may be something about the length of the paths, the types of nodes that occur in this graph. In that case, what it would probably learn is somehow representing that in its embedding that it learns. If you think about social networks, many of the tasks on social networks, essentially what helps is to say, make prediction about a node in a social network. You can think of it as like knowing something about the neighbors of the node. Like if you want to know something about me, knowing something about the, say, properties of my friends, their professions, their interests, or so, probably tells you something about me. So in that case, it's essentially doing some kind of advanced averaging over your local neighborhoods and representing your neighborhood. Like maybe some statistics about my friends and their friends would help you give you some information, additional information about myself. So in those kinds of cases, you would be doing this kind of more of like a neighborhood statistics thing. In some other cases, you really care about the structure, like the molecular tasks, presumably like who is connected to whom and in what way are there cycles or not is actually very important. So for those, you actually need some other ideas in encoding those. And if you think about the physical reasoning tasks, like learning a simulation, where you don't actually have a graph, you maybe make a nearest neighbor graph of your particles, and then you learn how the location of the particle is updated as a function of the location of the others or so. In those cases, you essentially learn like how in your simulation you go from one step to the next, the update of the states, which is like what this message passing learns in that case. Maybe that like essentially the function, how your next location depends on your velocity and the velocities of your neighbors and the location of your neighbors, etc. So those kinds of things is what you learn. So it depends a little bit on the task. what exactly this network is going to learn.
So what kind of data sizes are we talking about here? Because depending on to me, it's basically these things may be learning. When you're trying to learn dependencies, you're basically having to learn higher order moments, which of course all these things are nonlinear, which makes sense. But then inevitably the question of the sample complexity comes in. What kind of data do you need to actually have anything that's reasonable?
What kind? So yeah, you have your training data, and actually it really depends on the task. So some of the graph data sets are actually relatively small, even just a few hundred, the smaller ones. But then the way you're exploiting this is that you're sharing your learnable parts. So if you think about a convolutional network, one filter is applied, the same filter is applied like on all patches in the image. So that gives you like a lot of efficiency in the complexity with respect to data. So it saves you basically samples, and it saves you parameters. You have a few filters, but you apply the filters everywhere, and it's very localized, so they don't have as many parameters. So similarly, in a graph neural network, we're actually sharing, like each node applies the same aggregation function over its neighborhood. And so that's the shared part. So the actual MLPs in a graph neural network in practice, as I said, are not that large. So you basically learn only a few of these. In addition, of course, it's still like you still need a sufficient diversity in your data, etc., to actually learn the right things. And it's a bit task dependent.
Thank you.
So next question from Steven.
Yeah, hi, thanks. I appreciated the talk. So I asked this in the chat. I'm curious, I found in this space that making the right choices computationally is, very helpful and, above the theory. And I'm just curious, in your own experience, like, if you want to offer opinions, opinionated opinions about like what some of those right choices are for, like, if you thought, oh, I've got a graph and I want to do some classifier problem, and I don't know if it's going to work, and I want to download some stuff and get going quickly. Like, what representations do you think about using that makes this work out, or what packages, or is this space still very much DIY and I've got to implement all this in like, are you doing all this on TensorFlow or something else, or questions? I'm curious what your views are on choices like that.
Yeah, so there are actually a few libraries. I didn't actually put the links here. If you send me an email later, I can point you to some of them that implement some of these, like some of the more popular message passing algorithms in particular. So you don't have to implement everything from scratch. So you can use like Python, etc. if you want. There's also one from Amazon. So there's a few of these, and you could just use those libraries. In terms of types of graph neural network architectures, so I talked about those message passing architectures, and there's some popular ones. So as a sort of a general thing, you could try the one that I talked about earlier, which is this, it's called the GIN network, the graph isomorphism network, that does nonlinearity and sum and nonlinearity, that many people also use as a benchmark. That would be something you could try. There's some others like Graph Sage or so that people have used. And then there's fancier things that actually combine, say, some positional information and transformers or something like that. So go a little bit further. But I would first try like the cheapest message passing networks, essentially, before I go and do anything more expensive. In terms of the size of the network, so typically as I said, these are just like the aggregations are a few layers. So depending on what exact task you had, you could see what people have used like for a benchmark task that's similar and what worked there. That's like a good starting point if you want to say in terms of architecture tuning. But as with any like deep learning model, it's typically not that you like one works for all type of thing. You have to play a bit to get the right way to make it work.
Okay, and I heard the number of hundreds as an example. So does that mean like tens of thousands or hundreds of thousands is just too greedy for current capabilities?
So actually the like later benchmark tasks are larger because those first ones are smaller. So yes, computational complexity does play a role if you like say input graphs become very large in particular. And so the problem is if you run like iterations and your graph has very large degree, because you could look at this computation tree, it like branches out a lot. And so people have thought of strategies of making it more efficient. I didn't talk about them. But like say some of the companies that want to run it on really large graphs and want to make it efficient. So often what they do is they either do like they drop some neighbors or they limit the depth, how many iterations you go or so to keep it like tractable. Yes, so it is something to think about if you have like very large graphs, that it can become more expensive.
Thank you.
So Stefanie, there are also a few questions in the chat. I know that you answered some of them, but probably there are the last one, for example, from Willie.
Yeah, so about the heterophily, homophily. So the models I talked about, they mostly like, if you think about them as averaging neighbors or something like that, that would really go well with like the homophily and less with the heterophily. There are some works that also explicitly think about heterophily and how to make it work better for tasks that have that property. Many of the benchmark tasks do not specifically have that property, but that doesn't mean that it's not relevant. So there are some works that explicitly think about how to improve the architectures in that respect. And I also see there's another question: what will the GNN representation learn when it's trained on data that doesn't inherently have a graph structure? So the GNN needs some kind of graph structure in the sense that I have some neighborhood structure and somewhere I have to give it that. So I could just make that graph structure by saying I have, say, a set of particles and I connect the nearest neighbors or so, in which case you're sort of doing essentially a geometrically local averaging type thing. So it's still using the geometry of your data. If I have just a set of items and there's no order in it, I could still have the fully connected graph, as I said, and that actually also tends to work well for some tasks. In that case, it's mostly the type of reasoning that the network implements, in the sense that if it's a task that for which it's really good if you do like pairwise comparisons between your nodes or your items, let's say, if there's no nodes, and you do like iterative reasoning essentially with pairwise relations, then this is a really good architecture, like just do a fully connected graph and do a graph neural network over it, where you basically learn how to compare those different items. So just basically comparison between all items, like an advanced type of comparison. So that's sort of how you can think about it. So implicitly, how you feed the data into the network is how you think about the data as a graph. If you have no graph at all, you just have one data point, you would just be running your MLP, no neighbors. Well, that's just like a small, fully connected network, and you could basically stop after one iteration, or like each iteration would be just using the same node again. So for a single point, it's essentially just a feed-forward network.
Any other question? Maybe then I can ask a last one if there is no other question. Stephanie, you talked about these algorithmic tasks, but so I was wondering, how do these all extrapolation results generalize when you have also features on the node of the graph?
So the extrapolation results, it's the same thing. So basically, either your training and test data look the same in the range of the node attributes and the degrees, and basically anything that your function sees. And then in that way, in that case, you extrapolate automatically well. Like say, if the computation trees always look the same in your big graphs and small graphs, it's okay, it'll work. In the other case, you can talk about extrapolation if any of the following occurs, like your node attributes are in a different range, or your edge attributes, if you have them, are in a different range, or your degree distribution is different, or your graph is larger and hence your degrees are different, or something like that. So any of these, if one of them occurs, it can already basically take the aggregation functions in your graph out of distribution. And hence any of these would, for any of these, it would apply. And like, if you think about that, your nodes have attributes specifically, if you think about what I said about the aggregation function, in some sense, in the first round, you're applying this aggregation function to these node attributes as inputs. So in that case, already you would be out of distribution. So you would already be applying essentially that linear function, and maybe just doing like a sum over, like a weighted sum over those node attributes. So it would be the same thing. So as soon as your node attributes look different in the training and deployment data, let's say, then you have to worry about extrapolation and what your network does, or the modules in your network do when they see something that they haven't seen before, essentially.
Okay, thank you.
Does that answer the question?
Yes, thank you. And I guess there is a last question also in the chat. How will the extrapolation apply to weakly supervised graph learning? For example, a subset of graph nodes have both data and labels, but the rest of the graph nodes do not have labels or don't have data and labels.
Yeah, so I think that would be the same story in the sense that you look at all the nodes that have labels. So in that case, what you presumably want to predict is node labels. So basically each node and its surroundings, its neighborhood, would be a data point. So the labeled ones could be your training data points, and the other ones are essentially your test data points. If there is some kind of systematic difference between these labeled and unlabeled nodes, because maybe those were unlabeled for a reason that it was harder, and there's like some reason because their features are different or their neighbors are different or something, then you may actually have the same extrapolation problem. So as soon as now the distribution of the labels and the distribution of the unlabeled nodes looks different, you have a problem. And that is basically, now you can think of the distribution of those. If in each node you would build a computation tree, if the distribution of those computation trees is different in the training and the prediction, wherever you do the prediction, then you have a problem. And that could be in terms of structure or in terms of the attributes that you have for those nodes. So in either of these, it would be essentially the same story. So this applies to the full graph prediction or also for the node level prediction.
Okay, so I think we are going a bit over time. So unless there is any other urgent question, which I don't see in the chat, let's thank Stephanie again for this very interesting talk. And thanks everyone for attending. We hope to see you again in 2 weeks with our next paper of the